Again, welcome everyone, and we have a new topic now, which is part of the transcendental functions. Now, how to find the derivatives of a logarithmic functions. So before the formulas, now, try to recall the different properties of logarithm, the laws of exponent, and the laws of radicals. So we have two formulas now, in addition to the previous 22 formulas. Now, so we have derivative of any logarithmic functions u of base b. So that's equal to 1 over u, a logarithm of e base b, du dx. And if your logarithm is a natural logarithm, so we have the d24, which is the derivative of L in u, which is 1 over u. Actually, there is still a middle factor here, which is the logarithm of e, which is also containing the same base of e when that's ln, and the value of which is 1. That is why it does not appear anymore in d24, no? Because the middle factor is just equivalent to 1. So, the derivative of L in u with respect to x is equal to 1 over u du dx, where u is a differentiable function in x. Now, if you are given a problem like this, so you have a logarithm that is raised to a power, okay, so you may treat this directly as your u. So base is 3. So you may differentiate directly using the d23. Okay, so what is our u? Our u is the function that is having an exponent of 4. So we have the 4x cubed minus 5 raised to the 4th power. The derivative of which under a power rule is equal to 4 times the quantity 4x cubed minus 5 raised to 3. Then take the derivative of your function, that is 12x squared. So following the d23, so dy dx is 1 over u, including the power. So we have a logarithm base 3 of e, then multiplied with the derivative of your function u, which is 48, that's 48x squared, with a quantity 4x cubed minus 5 raised to 3. But this is appearing twice, so I can reduce, no? So we have 3 here, and this is 4. So what is left is the 4x cubed minus 5 in the denominator side. Okay, so you can have this as your final answer. The numerator is 48x squared logarithm base 3 of e over the 4x cubed minus 5 as our answer. But problem like this now may also be solved by applying first a property of logarithm to simplify our approach. Now, there is a property of logarithm. Okay, we have 3 here. The logarithm of a product, which can be broken into a logarithm of a sum. No? If you have a product of u times v, so you can have a logarithm of u plus the logarithm of v. When you have a ratio, u over v, so you can have a difference of 2 logarithmic functions. When you have a logarithm of u raised to a power, so you can have an exponent be taken as a factor first. So the definition also relating a logarithmic function with an exponential function, so we can have this as the definition. The logarithm of x base b is equal to y if and only if b raised to y is equal to x. Your b here must be greater than 0 but not equal to 1. Okay, now, so this can also produce a simplification formula by replacing your x with by. If this is x and your x is b raised to y, then that's equal to y. So, what does it mean? So, you can have a simplification formula that if these two numbers are the same, with the base used in the logarithm, the power of which will serve as the simplified form. No? So, if you also have an exponential, this is b raised to y, and your y is equal to a logarithm of x base b. So if these two are the same, then this expression will also serve as a simplified form. Okay, so actually, that is based from the definition of a logarithmic function, no, equivalently expressed in terms of an exponential form. Now, following the properties of logarithm, so I can simplify first before ako siyang i-differentiate. No? So, if we have a logarithm of u raised to power p, then that exponent can be taken as a factor. So that's what I did when this is raised originally to 4. So my 4 is now taken as a factor of a logarithmic function. So my u is only the 4x cubed minus 5, the du dx of which is 12x squared. And following the same formula, okay, so we have a dy dx. So we have 4 constant factor, and we have 1 over u. So 1 over u, our u is the 4x cubed minus 5, the logarithm of e base 3. So multiplied with the derivative, the du dx, which is 12x squared. Taking the product, we have 48x squared logarithm of e base 3 over 4x cubed minus 5 as our derivative. Now, in number 2, so the given may be simplified by first following a property or a law in radicals, then later a property in logarithm. Okay? So this is actually sine raised to 3, and then there is a radical whose index is 2. Okay, so how to simplify? And the law in radicals, which is asa, this one. If there is a power m here, and the index is n, then we can also write that as e to a power m over n. So that would mean that we have ln our sine of 3 halves. Okay? So if 3 halves is a power, then the power can also be taken as a factor according to property of logarithm. So we can now proceed under D24. We can take the derivative of the ln of, or the derivative of a product of 3 halves ln of sine of 5x. Okay, so 3 halves, 1 over u, our u is the sine 5x. Okay, 1 over sine of 5x, then the derivative of sine of 5x is cosine 5x times 5. Okay, so multiplying the constant, we have 15 over 2, and cosine over sine, we also know that it can be expressed in terms of cotangent under the quotient identity. Okay, so number 3. In number 3, if we have 10x, actually 10x here is raised to power 1 half, and entirely, this is also raised to power 1/3. And according to law and radicals, we can write it as, no, 1 radical symbol with the index which is a product of 2 and 3. So we have the 6th root of 10x. So if that is raised to power, that is equivalent to 1 over 6. So 1 over 6 can also be taken as a factor. This time, our logarithm does not indicate a base. When the base is not indicated, then this is understood to be classified as a common log or a Briggsian logarithm. There are 2 types of logarithm. We have the Briggsian or a common logarithm, and we also have the Napierian or a natural logarithm. Okay, now differentiating our y with respect to x. Actually, this is simplified according to this property or law and radicals design. Okay, so I take it in 1 radical symbol where the new index is the product of the 2 indices. No? So, m and n. So, the 2 index used are 3 and 2. Okay? So, differentiating 1 over 6 as the derivative, dy dx is equal to 1 over 6, 1 over u. What's our u? 10x. 1 over 10x, logarithm of e. The Euler's constant. Then, derivative of 10x is 10. 10 over 10 is eliminated, or it becomes 1. So, the final answer can be a logarithm of e over 6x as our answer. Now, in number 4, we are given a function which is containing different type of functions. There is algebraic, there is an inverse trigo, there is a logarithmic function. So, before I'm going to differentiate this in order to avoid using the law involving square roots, no? Or maybe involving power, so we can simplify first our logarithmic function. Okay, so in terms of fractional power, entirely this is raised to power 1 half. So 1 half, according to property of logarithm, can be taken as a factor. Then we are now ready to differentiate when your u in the logarithmic function is raised to a power which is now 1. Okay, product rule for the first term. So it is x. Arctan, derivative of arctan. Recall, it's 1 plus u squared. Okay? But your u is x, the derivative of which is 1 plus arctan x. Then derivative of x is 1. Second term, minus 1 half. Then 1 over u. 1 plus x squared. Derivative of x squared is 2x. 1 becomes 0. 1 half of 2 is 1. By the way, if you notice, my first term is x over 1 plus x squared. This is minus x over 1 plus x squared. So, the first and the last term is actually an additive inverse. So, sum is equal to 0. So, what is left is only the arctan of x as our answer. Number 5. Okay, this is an implicit differentiation. And I have to point out important part of this solution. Okay, so if we have a logarithm of a product, we have xy, and this is entirely raised to 2. So we also have that's equated to sign of the same expression xy. So you may go directly to this, no? So we have to simplify first using a property of logarithm. We have 2 ln of xy, and in order to avoid using a product rule, so we can also express this into sum of 2 logarithmic terms, ln of x plus the ln of y, all multiplied to 2. Now differentiate implicitly. So there is 2 times the derivative of ln x times the derivative pa of ln y. So we have 1 over x plus 1 over u, which is y prime. Because this is under implicit differentiation, your y prime will actually appear in a term involving y. We have a derivative of a sine function, which is cosine of xy as your u. Then we can differentiate under a product rule. X, y prime plus y times 1. Okay? Now, if I'm going to combine them as 1, there is a denominator or the LCD of xy. So, xy divided by x, we have y plus. So, divided by y, so we have xy prime. Okay? Then minus. So, I want you to notice that the expression of y plus xy prime is appearing common between the two terms. So, what we did previously is to factor out the y plus xy prime. So, removing the y plus xy prime as a common factor, what is left in the first term is 2 over xy. In the second term, I have cosine of xy equated to 0. Now again, a factor that contains the y prime is the one which will give you the derivative of your function. The other factor which is free from y prime will be disregarded. So y plus xy prime, equate that to 0, and you solve for the y prime, then you obtain an answer. But the best way for us to do a problem like this is to first notice that there is a reoccurring expression in every term, which is the product of xy. Correct? So I have an xy here. I also have an xy here. What is the advantage of having this be noticed at the start the problem was given? Because it is from this expression where the derivative can be taken. So, to continue, differentiate the xy with respect to x and equate the result to 0, and you solve for the y prime. Okay, so what is the derivative of xy? It is xy prime plus y equal to 0. Thus, your y prime is equal to minus y over x. Actually, no, ato-ato rin nyo manipangan, kung naghinambog lang sa ko, ako lang sa kita ko, just call this. Okay, di na ako basahan ka muna lang, no? Kaya mura gahinambog ko gamay. Okay, bitaw. I did not say this in any other book, no? So ako lang na siyang na-notice when I solve the problem that if there is an expression that is appearing common, no? On the terms involved in your equation, then the derivative of which, no, can be taken directly, and it is there where your y prime can be taken. Okay? So, thank you for following, and thank you for watching. Okay? So, bye-bye.